going to say, let's say it's 1 to 10. So for every gram of carbon-14, there's 10 grams of carbon-12. This is actually way more. It's a much smaller fraction, but the method is exactly the same. Carbon-12 is stable, so it stays the same for the whole time. So so what we have is, say for instance, we start with a material that has 2 kilograms of carbon-12 and 100 grams of carbon-14. We can do that, and that's currently. We can say, well, in the past, how much of each was there? Well, in the past, there was 2 kilograms of carbon-12 because it is constant. So that hasn't changed. In the present versus the past, that hasn't changed. But in the past, we're going to say that normally, so imagine that in the material now, let's say we made paper out of the plant, so it doesn't maintain this 1 to 10. So what we have here is we'd have 200 grams originally. This is the 1 to 10 ratio. So which means if we're starting with 200 and we go down to 100, that's 6,000 years. So now we can say that the material is 6,000 years old. This method of dating a material, so with carbon, is used to date things that once had an organic origin. Things like bones, things like paper or cloth. It was used to show that the Shroud of Turin was not the burial shroud of Jesus, so it was not 2,000 years old. It was shown to be about 500 years old, which puts it well in the medieval period, for which there are similar artifacts that were around from that point. So it can be used whenever you deal with organic materials. Now, if we're trying to measure the age of the Earth, carbon dating won't work for 2 reasons. One is that any given rock that has carbon in it, we don't know what the original amount was because it is not a biological process. We don't actually have a clue, like knowing the normal fraction of carbon 14 to carbon 12. Further, with a half-life of 6,000 years, if the Earth is millions to billions of years old, the number of half-lives would be so enormous that there wouldn't be anything left. So there wouldn't be any carbon-14 left at all in order to date the material. So in order to figure out the age of material, you need to have something that has a half-life on the order of the age of what you're dealing with. Well, I mean, luckily there are materials that have such long half-lives. So one of these is uranium-238, which has a half-life of 4.5 billion years. We can do things like looking at, in a given rock, there may be several minerals. The ratio of lead, say, for instance, the 2 different forms of lead will be the same in some of them, and that lets, just like the carbon-14 example, lets us infer something later on. So in mineral B, for example, uranium-238 becomes lead 206, and this increases, where the lead 204 is constant. Doing this many times, we can get the age of the Earth and of many rocks very, very accurately. So here's a chart that shows essentially the different types of rocks that we get, and pretty much what we see is 4.5 to 5 billion years. And it's not just one type of rock. It's not just one radioactive material. It's many of them, and they're all consistent, and they all give exactly or very close to the same answer. That's when you know something quite solidly in science. So what geologists do is they use a combination of relative and absolute dating. And what they do is they have some sort of column, and they are able to relatively date all these things. Essentially, the things near the bottom are older, and then the things that are near the top are younger. And there may be certain events that happen where, like volcanic eruptions, and it'll lay a thin layer of ash, or an asteroid impact may lay a thin line of dust. Many times that ash is able to be dated because it has these radioactive elements in it, and they're able to do it. And so then you essentially get specific dates for specific events. So you have a relative dating, and then you have a few dates sprinkled in here where you know the actual date, and then you can calibrate the rest of the column in that way. Now, what if you wanted to measure the age of the universe itself? Well, in reality, actually, they can measure the ages of galaxies using the same radiometric dating. I mean, looking for the signals for that, using the spectrum for those materials, we can actually get the quantities of some of them, and estimates can be made of those. But the primary way of measuring the age of the universe is using the expansion of the universe. So what we have is, if we measure the spectrum of hydrogen, or we do a spectrum, what we see are these nice little lines. This is at rest, and in a galaxy that's, say, moving away from us, the spectral line is shifted to the right, and the more it's shifted, the faster it is moving away from us. And if we can find the distance, it was Edwin Hubble who first made a plot that looked like this. Essentially, the farther away a galaxy is, the faster it's moving away from us. And the fact that each of these little dots falls into this nice line, we can do the following. We can say, all right, let's take a galaxy right here. So its distance away from us is 1,000 mega light years. Okay? And its speed away from us, all right, is so its speed is 22 kilometers 1,000 kilometers per second. Okay. So let me just delete that. Okay, so the speed is 22,000 kilometers per second away from us. So if it's at this distance and it's going at that speed away from us, if we rewind the movie, we can just simply do time is equal to distance over speed, and we get the time that these galaxies were all on top of us was about 13.7 billion years. Okay, and this is the age of the universe. This is essentially the time, if you were to go back, that all the matter in the universe was concentrated in a single spot. This is an old this method was done in the 1920s and has really been perfected over time. We know confidently now, out several decimal places, essentially 13.72 billion years, that is the age of the universe. So that's how we know the ages of biological things. We can gauge the age of the Earth. We can get the age of galaxies, of stars. So stars within the galaxies. So we can get the galaxies themselves, and even the universe itself. And it all comes down again to a process that changes in time, leaves some marker of the change, and from that marker and our understanding of the process, we can infer the age of the particular object.